Um, Good morning, everyone. This is part two of um, chapter 13 lecture video, the chapter on chemical kinetics. Um, so we have covered um, the basic concepts of chemical kinetics in lecture video one, namely um, the method of initial rates to determine um, the orders of reaction, Mn, and also the rate constant K. We have defined the rate law, and now today we want to use those informations to to take a look at what is known as integrated rate laws. This is section 16.4 in your textbook. Um, so the title of that section is Integrated Rate Laws. Now, for a first order reaction, the rate law can be written as rate equal to K, which is the rate constant, times the concentration of the reactant A. But remember that A refers to the molarity or the moles per liter of A per in that equation. So it's the unit of molarity that we are using for A. And the integrated rate law for any first order reaction can be written as the equation that I've shown in this box here. So basically that's the integrated rate law. Now you need some calculus to derive that equation. We are not going to go through the equation, how it's been derived and the details of it, but it's basically based on some areas of calculus that we can use to use differential equation and derive that equation at the end. Now, so again, we don't need to know how this equation is derived. The only important thing for us right now is to memorize this equation and know how to use this equation, okay? So equation 5 has to be memorized. So that's the equation in this box here. There are three forms of the integrated rate law for the first order reaction that I have presented here. So basically they are the same equations. That's what I want to emphasize here. They are not different equations. They are the same, merely expressed in different forms. Okay? For example, the first ratio has A on top, A0 at the bottom. The second one, when we flip this ratio, the negative sign disappears. And in the last one, we basically expand this ratio in terms of the natural log, which becomes natural log of A minus natural log of A0 minus natural log of A, which basically becomes the equation of a straight line, which is presented in the last part of that equation. So all these three equations are basically the same, but merely expressed differently in different forms. Okay, so and I've also used this basic rule of a natural logarithm, that the natural logarithm of a ratio is the negative of the natural log of the inverse of that ratio. So in other words, if I flip this ratio, I have to introduce a negative sign and vice versa, which is basically what I've used here. And also for the expansion of the natural log of a ratio, I have used, in other words, from here to here. If you want to go from this equation to that equation, you have to use this basic rule of natural logs. So these are basically from algebra. Okay? Now let's take a look at the next slide. So again, we have to define some of these symbols that we are using in this notation. The A enclosed in the bracket means concentration of A at any time except time t equal to 0, because t equal to 0 has its own symbol, and that is A0. So A0 is the concentration of reactant A at t equal to 0, initial concentration. So basically it's known as initial concentration. So the symbol we use for initial concentration and the symbol we use for concentration at any time other than t equal to 0, they are basically different. One is A, one is A0. K is, as you know, it's the first order rate constant. Now the unit of K is 1/2, or the inverse of second. So s to the negative 1, or 1/s, is the unit of K. Now, we also note that this equation here represents the equation of a straight line. So it's a linear equation, y equal to mx plus b, where y and x are the variables, and m is the slope, and t is your variable as well. Okay, so basically this is the intercept, this is the variable. So ln A is plotted versus t to give you a slope, a negative slope of negative k, with the intercept of natural log of A0. Okay, so one of the reasons that I presented this last equation in equation 5 was to remind you that this is actually equation of a straight line. Okay, now so let me just make sure this is straight. Okay, now, so basically, again, I've described here that if you plot ln A versus t, the slope, which is rise over run, is going to be a negative slope, and it's negative k, negative of the rate constant, and the intercept is going to be natural log of A0. Now, we also have to define, in the context of integrated rate law, another term, which is called the half-life. The half-life of a reaction is the time that it takes for the reactant concentration to reach half the initial concentration. And it's shown by T with a subscript 1/2. Okay, so T 1/2 is basically, it takes up different forms, or we have different equations expressing T 1/2 for different reaction orders. In other words, if you go to a second order reaction, the T 1/2 equation will change. So for a first order reaction, again, we need to memorize this equation. The half-life, the time that it takes for the concentration to reach half the initial concentration, is given by a simple equation, 0.693 divided by k. Again, this equation can be derived from the integrated rate law, but we are not going to go through the derivation. We are simply going to memorize that equation. Okay, so there are two things that you need to memorize right now in connection with the integrated rate law for a first order reaction. One is equation 5, and the other one is the half-life equation, which is equation 6. Okay, now let's see. Second order reactions. For a second order reaction, the rate law can be written as K times the concentration of A squared. So again, we always start with the expression of the rate law for the that particular reaction order. So now the question is, what is the integrated rate law for a second order reaction? Now, similar to what we had for a first order reaction, the integrated rate law, after manipulating this equation using differential equation and some basic knowledge of calculus, we arrive at this equation. Again, that derivation is not important at this point, but what I want you to know is how to use this equation, and also be able to recall this equation and use it. So memorize this equation and know how to use it. So we will be going through some examples of how to apply this equation. So it's the inverse of the concentration of A, 1/A, equal to KT, rate constant, times time, plus 1/A A0. Now A0, remember, A0 is the initial concentration and A is just the concentration by itself. So this is the concentration at T equal to 0 before the reaction starts, and this is the concentration at any other time other than T equal to 0. Now, again, this is the equation of a straight line. In other words, if you plot 1 over A versus T, the slope is going to be K with the intercept of 1 over A0. Okay? Now, K is the second order rate constant, and the unit of K is 1 over molarity times second. So, again, the T1/2, or the half-life of this second order reaction is given by this equation, which I want you to memorize. Okay, so there are two equations that you need to memorize in connection with the second order reaction. One is the integrated rate law given in equation 7, and the other one is the half-life in equation 8. Okay. Okay, now we have a table in the textbook which is basically an overview of first and second order reactions, and that's table 16.4. So if you look at that table, you'll see basically everything that we just talked about summarized under first and second order reaction in that table. So in that table you see the integrated rate law, the unit of K, the graphical representation, and all that. So everything will be there in that table 16.4. Now, the next topic that we want to cover is called the dependence of rate on temperature. In other words, how is the rate of a reaction changes with an increase or a decrease in temperature. Now, first of all rates of chemical reactions are known to be temperature dependent. That means if you increase the temperature or decrease the temperature, the rate, the speed by which the reaction takes place changes. So the rates are temperature dependent. Now, this dependence of rate on temperature is shown by a famous equation known as Arrhenius equation, and that's equation 9 in that box. Okay, so again, memorize this equation. It's a very important equation. Now in this equation we have the natural log of the ratio of two rate constants, EA, which is called activation energy, divided by R, that's the gas constant. T1 is the initial temperature in Kelvin. T2 is the final temperature, again in Kelvin. So all the temperature must be expressed in Kelvin in this equation. Okay, now R is a gas constant. It's 8.314 joules per mole per K. That will be given to you. Okay. Now the subscript 1 and 2, they stand for initial and final. So K1 is the initial rate constant, K2 is the final rate constant. And T1 is the initial temperature, T2 is the final temperature. Okay, now we need to say a little bit about the activation energy, EA, that appears in that equation. Activation energy, by definition, is the energy threshold that the colliding molecules must exceed in order to react. In other words, if they do not have a minimum amount of the, by they I mean those reactant molecules. So if the reactant molecules, they do not possess a certain amount or a minimum amount of energy that they need to go from the reactant side to the product side, then the reaction will not take place. So it's a really, it's more of an energy threshold that these molecules must possess in order to react with each other and be converted to the product side. So that's called the activation energy. Now, this whole concept of the Arrhenius equation and the dependence of reaction rate on temperature is well demonstrated in sample exercise 16.8 on page 717. Okay, this is the decomposition of hydrogen iodide, HI, into hydrogen and iodine gas, and the decomposition reaction is given here, and the rate constant is 9.51 times 10 negative 9 at this temperature. So you always see this statement that the rate constant is such and such at this temperature. And then we change the temperature and we get a different rate constant. So basically, this is my initial rate constant corresponding to this initial temperature. So that's K1, T1. Now I am going to change the temperature from 500K to 600K. So that's my T2. And now I get a new rate constant, which is in my K2. So K1, T1. Now I change the temperature to T2, I get K2. Okay? So these are all given to me in the reaction, in the problem with respect to this reaction. So the question is, if I know K1, T1, K2, T2, how do I find EA? Okay, activation energy, given that R is 8.314. Okay, so everything is summarized here. Okay, now let's take a look at the solution to that problem, and you'll see that we start with the Arrhenius equation, and there are two ways to solve this. You can either just plug in the numbers from the problem and solve for EA, or simply just rearrange the equation the way I have done here to solve for EA first and then plug in the numbers. Okay, so it's totally up to you. But I would like, I think this would be a more straightforward and easier method of carrying out the calculation. So basically, this is the equation for EA. So basically what we have is ln of K2 over K1 times R divided by 1 over T1 minus 1 over T2. In other words, the first thing you can do is to multiply both sides by R. So you have this part here. And then that left side divided by the right-hand side that doesn't have an R, which is this, right? Okay, so now everything is given to us. We just simply plug in the numbers here. Now at this point, you need to use your calculator. And remember, when you're using your calculator, use the function, the exponential notation function on your calculator to carry out these ratios and also natural log. So everything you need to do here is basically these are separate functions on your calculator. You can easily verify this on your calculator to be 1.76 times 10 to the fifth. Okay, so that is the amount of activation energy. That's the energy threshold that is required for the reactants to have in order to be transition from the reactant to the product side. Okay, now the last topic is called reaction mechanism. A reaction mechanism is a sequence of single steps. Now those single steps are called elementary steps or elementary reactions. Okay, so it's a series of single steps known as elementary reactions. And those steps, those single steps, those elementary reactions, they must add up to give the overall reaction. So in other words, in simplest term, when you look at a reaction, the reaction doesn't just take place the way it's written. Most probably it goes through a series of steps. Okay, a series of steps. Those steps are called elementary reactions. And then when you add those steps, those single steps, then what we have is basically the overall reaction, and therefore the collection of those steps is known as the sequence of those steps is known as the reaction mechanism. Now, um, so there are two key points related to reaction mechanism. First, the single steps that we are calling elementary reactions, they have different rates. In other words, some of them are faster than the others, some of them are slower. So that is important for us to know, because the reason that we have to know this is because the one that takes place at a much slower pace or rate, so the slower one is called the rate determining step, RDS. So we always focus on the one that takes place very slowly compared to the other. The others are fast, one of them is slow. So we pick the slow one and we call that the rate determining step. And the reason we call it the rate determining step is because that one is going to basically control or determine the overall rate of the reaction. Okay. Now, we will be able to actually demonstrate this in the example that I'm going to discuss with you right now. And that is a very typical common mechanism where we have a fast initial step followed by a slow rate determining step. Okay, now that is one of the examples that has been worked out in the book, page 724. I don't believe this is a sample problem. The last time I checked, it was basically it's in the body of the text. It's not a separate sample exercise, so therefore I didn't call. It's just an example given on page 724. So this is basically the oxidation of NO. So 2NO plus O2 going to 2NO2. This is our overall reaction. Now, the rate law for this, which is the observed rate law, and again, as I mentioned before, this rate law is the experimental rate law. It's been determined by experiment. So it's called the observed rate law. And so this has been determined by method of initial rate. The reaction is second order with respect to NO, first order with respect to O2. Okay, and the proposed mechanism is given to us to be these two steps. So these two steps collectively is the mechanism. Now, as you can see, in the first step, which is a fast step and also a reversible step, and we are using this reversible arrow. One goes from left to right, the other one right to left. That is usually takes place at a faster pace. That's the reversible process. The second one is a slow, and also by definition it determines the overall rate of the reaction, so it's called RDS, or rate determining step. Okay, now so this is so each reaction or each step labeled as 1 and 2 is an elementary reaction. Okay, so step 1 elementary, step 2 elementary. Now when we add these two reactions, okay, what happens? When you add reactions, basically you cancel out the identical components on opposite side of that reaction, So NO3 product, NO3 reactant, you can cancel these, right? So this is how you add them. So if you cancel these two components and also add the NO with NO, you get 2NO, you get O2 here, and then NO3 is already canceled out with this one, and then you get 2NO2 on this side. So basically you get the overall reaction back. So remember we said that there are two key points about reaction mechanism, that we have to identify the slow step as the rate determining step, which we have done here. We know this is slow and it's going to determine the rate of the reaction. And also if you add the two elementary reaction, you must get back the overall reaction. And if you add these two, you get that one back. Okay, so I think in the next, and the question actually is prove that this mechanism is consistent with this rate law. So in other words, we're going to use these two steps or the mechanism to prove that the rate law that we observed in the experiment is correct. Okay. Okay. So this is how we prove that the mechanism is consistent with the observed rate law. Okay. So I've actually shown you how to add these two reactions first. This is what I just described to you. Okay, NO3 cancels NO3, and then you have two NOs adding up to plus O2 to give you that. So therefore, the first requirement is satisfied that the elementary reactions must add up to give you the overall reaction back. Okay. Now, next thing is we are going to use the rate determining step. Okay, we are going to use the rate determining step to verify if this mechanism is consistent with the observed rate law. Okay, now just a matter of notation. Usually for the reactions given in the mechanism, we use a K to describe the rate of that reaction. So K is basically used to describe the rate. So for reversible reaction, we have a K1 for the forward reaction and K minus 1 for the reverse reaction. And then for the next one, we call it K2. So because each reaction has its own specific rate constant. Okay? Now, from the slow reaction, which is the rate determining step, we write the rate law. So if you just focus on the slowest step, you see that the rate law can be written as K2, which is the rate constant for that particular reaction, times the concentrations of the reactants, NO3 and NO. Okay. Now, in here, we don't use M and N. We simply use the coefficients of that elementary reaction. So the only time we can actually forget about M and N and just use the coefficients as M and N is when you're dealing with a slow step in or elementary reaction in general in a given reaction mechanism. Okay. So this is elementary reaction. So all elementary reactions, the rate law for all elementary reactions can be written with respect to their balance coefficient given to us. So the coefficient of NO3 is 1, NO is 1, so we are using those actual coefficients here. That's the only time we can do that. If the reaction is not elementary, then we have to use M and N. If it's elementary, we use the coefficients given in that reaction, which is the case here. Now, and I've also indicated that for the reversible, we have K1, K minus 1, and for the other one, we have K2, okay? Now, so this is the rate law. Now, we are going to see if this rate law that we get from this mechanism based on the slow step is consistent with the rate law given to us in the beginning of the problem, the observed rate law. Now, in order to prove that, or in order to see if this is compatible or if this is a plausible reaction, we basically have to take a look at the components of this. Yeah, one of the components is NO3. NO3 appears in the fast step and then it disappears in the slow step. So, in other words, it's product in one step and it's a reactant in the other step. Okay, now those kind of components, they're called intermediates. So NO3 in this rate equation is an intermediate, is identified as an intermediate. Intermediate appears in the fast step, disappears in the slow step. Okay? Now, we, as a general rule, we don't like to deal with intermediates because usually they have unknown concentrations. Okay? And it's hard to measure their concentrations. They have a short lifetime. they appear, they disappear. So we don't want to base our rate law on a concentration of a component that does not have a well-defined concentration, or something that appears in one step and disappears in the other step, like NO3. So the intermediate, which is NO3, must be eliminated from this rate law. Okay. In the next page, I show you how to use the fast or reversible reaction to do that. So we need to get rid of NO3 since it's not stable. Okay. And now this, and we have to use the reversible step to somehow set up some kind of equation that we can solve for NO3, or basically replace NO3 using the reversible equation. So I have borrowed some key concepts from the next chapter, which is the chapter on equilibrium, and I've placed it in this box, equation 10. Now, when we start chapter 17, you'll see that for any reversible equilibrium reaction of this type, okay, where I'm using Kf for the forward reaction, Kr for the reverse reaction, okay? Usually the fast reversible reactions are at equilibrium, okay? Now, when equilibrium takes place, when equilibrium is established for a reversible reaction, this is the condition that needs to be met. In other words, the rate of the forward reaction must balance out, or must be equal to the rate of the reverse reaction. Okay? So the F stands for forward, R stands for reverse. By forward, we mean A going to B. By reverse, we mean B going to A. Okay? So, and similarly, Kf is the forward rate constant. Kr is called the reverse rate constant. So, if Kf times A, in other words, the rate of forward reaction, must be equal to Kr times B, or the rate of the reverse reaction, then we can easily substitute for either A or B in terms of the other component, or solve for them in this equation. So we're going to apply this equation 10 to our problem. Okay? And in the next slide, you'll see that, or in the next page, you'll see that we can apply that over here for this equilibrium reaction, fast reversible equilibrium reaction. So, okay, so I'm using basically the equation 10 here. K1 times NO times O2 equal to K minus 1 times NO3. And then we are going to solve for NO3, because that is our intermediate and we want to get rid of it. We want to basically solve for NO3 in terms of the other components, namely NO and O2. So I'm just solving for NO3 here, NO3. So I'm basically dividing both sides by K minus 1. That's all I'm doing to just isolate NO3. So NO3 is equal to K1 divided by K minus 1 times NO times O2. And I have intentionally written the ratio of the rates in one term. So now if you substitute this, okay, if you substitute this NO3, which is now here, into the old rate that we had, law that we had. Remember, this was the old rate law, okay? And we said this NO3 must be replaced. So now I'm going to place this for NO3 here, okay? So remember, NO3 is equal to this. Now I'm going to, instead of writing NO3 here, I'm just going to use this whole expression and place it here, okay? So in the next page, you'll see that this entire thing is the NO3 that we solved. So now if you multiply K2 by that, you see that becomes K2, K1, K minus 1. And we're going to collectively call all these rate constants as K, because after all, they are just constants. So the ratio of two constants times another constant is going to give you a separate constant. We're going to call it K. It doesn't matter. Okay. So we're going to call all those K's collectively as just one single K. And the rate becomes K times, so this is K times NO squared times O2. So in other words, I'm replacing, I'm kind of cleaning up this equation here. K2, K1, K minus 1, I'm going to call it K right here. NO times NO, that's NO squared. And then O2 that I've left with. And this is exactly what we had as the observed rate law given to us in the beginning of that sample problem, okay, or that example that we had. Okay, so therefore we can say the conclusion here is that the mechanism given to us is actually a plausible mechanism, is consistent with the experimental rate law. Okay, that brings us to the end of chapter 16, chapter on chemical kinetics, and the next video will be about the chapter on equilibrium. Have a great day. I'll see you later.